In this session of the electromagnetic theory for LMS systems, we are going to discuss the fourth Maxwell's field equations. That means among the four equations, this one is the last equation. Just recollect uh, the first three. The first one is divergence of E is equal to rho by epsilon naught. That means the origin of the electric field, the charges. Second, divergence of B is equal to 0. That means the magnetic field is not produced due to a magnet, but it is due to the flow of the charges or a current, or in general the magnetic monopoles are not existing like the isolated positive charge or negative charge. Similarly, the magnetic field lines are discontinuous. That means it always magnetic field lines are continuous. There is no breaking. It is an endless. So that's what we studied. And in the third Maxwell equations, we studied del cross E is equal to minus dou B by dou T. That means whenever the magnetic flux changes, an EMF or an electric field is going to be produced. So everything in the nature is symmetrical. If the variation of the magnetic field with respect to time an electric field is going to produce, then naturally the electric field variation should produce a magnetic field. Okay, so now that is what we are discussing in the case of the fourth Maxwell equation. And the very important idea here is, so far we studied the current means the flow of the free charges. That means the current through conductor or the conduction current. So in nature, it is not just the conduction current, there is also the other type of a current. So that's what we are going to discuss here. That means if you take an example of a capacitor, if you connect it across the source, then the capacitor charges. Thereafter, until the charging is taking place, there is a current. Thereafter, capacitor blocks DC, whereas the same capacitor allows the alternating current. So how come it is possible? The plate between the two capacitors, plate between them, the medium is dielectric, or the medium is going to be vacuum, or it's an air, then how there is a flow of charges. So that's what the new type of a current we are discussing. So in order to understand that, you just go through this Ampere's law. Okay, so that Ampere's law is written in vector form. The line integral of magnetic field B around any closed path is directly proportional to the current. That's what we have studied, the Ampere's circuit law or the Ampere's law. The line integral of magnetic field B around any closed path is directly proportional to the strength of the current. So this is the mathematical expression where mu naught stands the permeability of the free space, the I stands the strength of the current, dl stand the length of an element, B is the magnetic field strength. Okay, so this is according to the Ampere's law. So you know the current, total current is nothing but J dot ds. What is J? The current density. Current density means what? Current by area. So that's called the current density. Current by area multiplied by area, if you are doing, then you are going to get the current, total actual current. So that total current I is expressed in vector form as J dot ds. ds is an element of an area, J is the current density, and then mu naught permeability. Remember, J current density, that is nothing but current by area. If you multiply by area, area cancels, this is true. So this, in the place of I wrote this particular term J dot ds. So this equation becomes like this. The left hand side I wrote it here, mu naught J dot ds. So understood? In the place of I wrote this. Okay. Now you just, by Stokes theorem, you just go through the previous. Here one side is a surface integral, the another side is a line integral. Okay, so that equated B dot dl is nothing but del cross B dot ds. So this arrow mark is unnecessary when you are writing del cross B. Here also vector is there, here also vector is there. Don't bother about this vector notation. So this is according to the Stokes theorem. B dot dl is equal to del cross B dot ds. So in the place of B dot dl in the previous equation, B dot dl, I'm going to write this del cross B dot ds equal to mu naught J dot ds. Okay. So now therefore the both surface integral you can equate it. So when you are equating it, del cross B is equal to mu naught J air or vacuum for any other medium, then it is going to be mu stands the permeability of the medium, mu naught stands permeability of air or vacuum. So these two related, mu is equal to mu naught into mu r. So this is in general for air or vacuum, del cross B is equal to mu naught J. Okay, so this is what we thought, similar to our third Maxwell equation, del cross E is equal to minus dou B by dou T. So what you understood here is, at this point is, suppose there is a current, J stands the current density, there is a current, then magnetic field is going to be produced. This is everybody knows factor. The current, magnetic. How current is produced? Because of the flow of charge. When charges are flowing, whenever potential difference is there. When potential difference comes because of the constant electric field. Okay. So electric field establishes potential difference, makes the charges to flow. So therefore there is a current. Therefore in that region the magnetic field will be produced. So this is, we knows it, there is no problem of it. But the difficulty arises when we are taking the divergence of above equation. To this equation, if we are taking the divergence of this term, okay. So divergence of this, understood? Here also divergence is taken. So mu not taken outside. We got this divergence day. Divergence dot del cross B, del dot del cross B. Okay, so vectorially this is going to be 0. Del dot del cross B 0. So what happens if this is going to be 0? Then this particular part mu naught del dot J should be equal to 0. Okay, see this is simple mathematics. So I brought it here. I got del dot J is equal to 0. Now you see, here lies the trouble. Just go through the equation of continuity. What it says, del dot J plus d rho by dt equal to 0. According to this idea, this part is 0. Then this is going to be 0. D rho by dt equal to 0. Okay. This is a very important step. See, A plus B equal to 0. Nice. If I am considering A as a 4 plus, then B should be minus 4 equal to 0. That's fantastic. There is no doubt about it. This is my A, this is my B equal to 0. A plus B equal to 0. It is mathematically valid. If it is not, see, just take this. This is 0. What is left? B equal to 0. If B equal to 0, then there is no meaning to it. Okay, I will come back to this point a little later. B equal to 0, there is no meaning. A plus B equal to 0, that equation has the meaning. A is 4, if I am considering, B is minus 4, then A plus B equal to 0 is a valid one. If this term is not there, this is equal to 0, one option is there that I will speak little later. B equal to 0, there is no meaning to it. Or you may say, sir, differentiation of a constant thing is going to be 0. But we said there is a flow of charges. Whenever there is a flow of charges, this rho is not going to be constant. So the re rho by re rho is going to be 0 is not possible. But this equation says d rho by dt equal to 0. What is the meaning? Total flux of current out of the closed surface is 0. The current is entering, then the current should leave. The charges must enter, the charges must leave. But this says the total flux of current out of the closed surface is 0, which is not true. If the current is entering, then only the current is leaving. If the current is not entering, there is no question of it. So del cross say, this says the total charge entering equal to total charge leaving. Okay, if this is going to be 0, then the total charge leaving is 0. That physically we cannot understand it. Or mathematically A plus B 0, okay, A I can consider 4 and B is minus 4, then there is a meaning to it. Just a term B equal to 0, there is no meaning to it. That's what the difficulty arises. So when we are saying del cross B equal to mu naught, if you just say J only, then this difficulty arises. These difficulties. There is actually the conservation of the charges, but this violates that conservation of the charges because charges are not entering, the charges are not leaving. If the charges are entering, then we cannot say charges are not leaving. The current is entering, we cannot say the current is not leaving it. We have to say the current is leaving. Okay, so this is the discrepancy or the difficulty arised in the previous equation. This del cross B is equal to mu naught J if you are considering this much only. Okay. So in order to overcome this difficulty, Maxwell introduced a one more term J dash. Okay. This is the again a current density because this is current density. This is also current density. A new term correction factor was introduced by the Maxwell. So when this is introduced and again the same divergence is taken, then the equation reduces. See, this part is 0. So mu naught divergence, this is going to be 0. If you proceed further, divergence d dash equal to minus divergence j. Okay. Then this divergence d dash equal to minus of minus d rho by dt because according to this term, divergence j is equal to minus d rho by dt. So if you take that here, divergence j is equal to minus d rho by dt, we are getting divergence j is equal to minus of minus, okay, plus. And we know rho is nothing but del dot. This is the first Maxwell equation. That you substitute here. What are you getting? Divergence j dash, a current density, equal to this. Okay. So in this, you can take del outside, then it becomes divergence d rho d by rho t. That means divergence rho d by rho t. So after comparing, again I will go through this equal to minus divergence j is nothing but d rho by dt. So substitute it here. You are getting divergence j dash as d rho by dt. In the place of rho, according to first Maxwell equation, you substitute del dot d. That becomes this. You can take this del outside, then it becomes del dot d rho d by dou t. Del dot rho d by dou t. So after comparing, you are getting j dash is equal to dou d by dou t. This is very important. This it is a correction factor introduced in the previous equation to the already known conduction current density. Therefore, this should also a current density. So this is when the free charges are flowing. We don't know the nature of this. Okay. Now here it is a meaning. J dash is equal to rho d by dt. In the place of rho, in the place of d, you write epsilon naught. Then it becomes epsilon naught rho e by rho t or dou e by dou t. Again, d you write this, then it become dou epsilon naught e by dou t. What is the electric displacement or displacement vector? That is nothing but this. So when you took epsilon naught outside, j dash becomes epsilon naught rho e by rho t or dou e by dou t. Understood? It was written here epsilon dou e by dou t. This is the equation you are getting it here. Now look at this is an interesting one. This is current density. This is also current density. This is because of the conduction current density sigma E, where sigma stands the electrical conductivity. This is the current passing through the conductor. Whereas look at here, even when there is no current, look at this is E constant, conduction current density is there. Suppose E equal to 0, J value is 0. That means we says if there is no electric field, there is no conduction current. Okay. What we are observed here is in the region if the electric field is varying, then again a current is produced. Okay, so this is an important one. If the electric field is constant, conduction current. If there is no electric field, then no current at all. That's a conduction current. Suppose in the region, the electric field varies. This is interesting. The electric field varies with respect dou E by dou T. Then it establishes a current. Okay, that is called displacement current, and the corresponding density is the displacement current density. Understood? Whenever the electric field varies in a region, then a current is established. That's called the displacement current, and the corresponding density is called the displacement current density. So this is the new term or a correction factor introduced by the Maxwell to overcome the discrepancy in the violation of the conservation equation of continuity. So this idea was not there. Now a question arises whether this type of current is existing or not. Okay. So in order to understand this, okay, this is a final Maxwell equation, del cross B mu epsilon. It is in general the fourth Maxwell equations. Okay. Magnetic field can be generated by the current density vector time variation of D jointly as well as separately. Remember, in any region, we can produce the magnetic field using the normal conduction current or the variation of the electric field. So, by both the methods, we can produce a magnetic field. If there is just a current, magnetic field is produced. If there is a just variation of the electric field, again the magnetic field is going to be produced. Magnetic field. Just current, magnetic field produced. Just variation of electric field, magnetic field. Both are there, then again the magnetic field is also produced. This is what we have seen in the case of a electromagnetic waves, electric field disturbance and the magnetic field disturbance. So electric field disturbance induces the magnetic field disturbance, and the magnetic field disturbance induces the electric field disturbance. Now the difficulty is, what is the nature of that displacement current, where it is existing? Okay, so this we have to understand it. So imagine the capacitor. You connect it across the source for charging purpose. So when the key is closed, the DC source, the capacitor gets charged. That means charges stored one plate positive charge, the other plate negative charge. So as the process of charging increases, more and more charges are going to be stored until the capacitor is fully charged. So this is we are saying dq be the charge on the plate of the capacitor during the time dt. That means the when capacitor connected to DC source, key is closed, the one side positive charges are deposited, on the other plate negative. That's what we say. dq be the charges on the plates during the time dt. Therefore, the displacement current, flow of the charges here, displacement current id dou q by dou t. Okay. So this q is nothing but in capacitor C into V. So this C is nothing but epsilon A by X. A stands the area of the cross section, X stands the distance of separation between the plates of the capacitor. But we know the potential difference by the distance is nothing but the electric intensity. E is nothing but dV by dx. So in the place of E, V by X we can write, or in the place of V by X we can write E. So that what happens, Q is equal to epsilon AE. So this is the displacement current during the process of charging of the capacitor between the plate. So we observed there is a change in the quantity of charge stored dq by dt. Look at q is C into V. C is nothing but A epsilon by X. V by X is nothing but the E. So that's what we wrote here. Q is equal to epsilon A E. This is we written in the place of a Q. Epsilon is constant, A is constant, we took outside, epsilon A dou E by dou T. Okay, this is the equation for displacement current density. What it says, whenever the electric field varies with respect to time, a current is produced, that is called the displacement current, not the conduction current. Okay, so this flows in the region where there is a vacuum or where there is a dielectric or where there is no conducting medium. Okay, remember this. Now, current density is nothing but current by area. ID by A. Current by area. Current is how much? Epsilon A dou E by D. Divided by area you do it, A cancels. So this is, okay. This is an expression for displacement current density. This is an expression for displacement current. So what is the difference between the conduction current and the displacement current? Whenever the electric field varies, there the current can also be produced, that is called the displacement current, where that means it doesn't require medium, just vary the, okay, it's similar to the movement of the dipole in between the plates of the capacitors. Okay, so that's what we are observing here. The displacement current is accompanied by the changing magnetic field. So whenever electric field varies, displacement current is produced. Whenever there is a current, a magnetic field is going to be produced. So electric field changes, the displacement current is produced. Displacement current is accompanied by changing of the magnetic field. So in general, we can conclude from the fourth Maxwell equation, momentary magnetic field will produce an induced EMF. Okay. So whenever the magnetic flux changes, an EMF is induced, which in turn produce a new displacement current. And this in turn will produce a magnetic field, or magnetic field produces the electric field produces the magnetic field, or there is a mutual generation of electric and magnetic field. So the displacement current is produced an electromagnetic disturbance which will propagate in all direction from the region of displacement current. So this is what the conclusion we are drawing it. Displacement current is produced, an electromagnetic disturbance will propagate in all direction from the region of the displacement current. So in the fourth Maxwell equation, we understood the 2 points. One, the current, different nature of the current. So one is the conduction current, the other is the displacement current. Even when there is J0, conduction current 0, there may be a current due to the variation of the electric field. So this idea, try to understand it properly. Okay. So thank you. With this, I'm going to stop my discussion. In the next class, next session, I'm going to discuss how the electromagnetic disturbance is propagating through the medium. What is the speed of it? Okay. So thank you.